So if you've been following along, you've seen one of these. I guess that makes this 4 times as good, doesn't it? Now, I do have some tragic news to impart upon you. I was faffing about with this since the video I did about it, and I had my power supply set at 5 volts and 1 full amp as I was messing around with some things, and decided to start connecting some of these. And I seem to have forgotten the resistor in the circuit because my power supply turned on its cooling fan for a very brief moment. There was a very brief flash, and now the middle segment, has gone to the great silicon mine in the sky. But I can still make a nice circular progress indicator out of it, or something like that. 5 volts times 1 amp equals 5 watts. And trust me, 5 watts through an LED is a lot of watts. We shall now have a moment of silence. And now, onward to the future. So we figured out that this one, the little one, the single digit, has 10 pins. 2 of them are common cathode, and the other 8 are to the different segments. The 7-digit segments, which is why it's called a 7-segment display, and the decimal point. So this one has 12 pins, 6 on each side. So now, of course, we're doing this without the spec sheet again. Now we have to figure out, we have 8 times 4 is 32 segments to control with 12 pins, whereas on the other one we had 10 pins to control 8 segments. More pins, more things to control than you have pins usually means there's some trickery involved, and you'll need to check the spec sheet. But not quite yet. There is trickery involved, but nothing so interesting as a shift register. There's no step-by-step. It's actually still pretty simple. So what do we have first of all, if we're trying to decide whether we should even bother trying to figure it out? Well, we have 32 segments. That happens to be 2 to the 5. So we can encode that in 5 bits. Well, we have 12 pins. Let's say we have 5 pins representing those 5 bits, that 5-bit number. 1 more for a common cathode or anode. That's only half the pins. So we already know it's certainly possible to do this with some sort of trickery. So I say we give it a shot. So step 1, we assume that it is a common cathode or common anode LED array just like the other one. So we first have to figure out whether it's common cathode or common anode. If we can't do that, then that means it's more complex and we give up and go find the spec sheet. But if we can, then we can start figuring out how it's wired up. So I have here my breadboard with my power supply, 5 volts, no amps, a 1K resistor, which I will be very careful to actually use. This is fortunately designed for a breadboard, so it has the correct spacing of pins, 6 on each side, and I'm just going to put this across one of the middle bridges, and I'm going to do it apparently upside down. Let's try that again. I've put it in so that the top left pin is on 10. It's just numbered 10 right there. And then that means the bottom left pin is an upside down 50, just so I know without having to dig down where the pins are. So the 6 on each side, we'll call them 1, 2, 3, 4, 5, 6 on the top, left to right, 7, 8, 9, 10, 11, 12 on the bottom. So I will now take 2 wires. So I got this in the same kit as the other one, and it looks like it's manufactured in the same way, it's just bigger. It's the same color and shape and everything. So that one was common cathode, so let's just assume this one is common cathode as well. If we turn out to be wrong, then we can just test it for being a common anode. But for common cathode, I'm going to go ahead and put the negative power rail through a resistor. The resistor is important. And for actually using an LED array, as you recall, we need separate resistors for each pin. But I'm only going to be testing 1 pin at a time, so we'll just go ahead and do this and put it on the cathode so I don't have to keep moving it around. And then we'll take the positive rail. Now how I'm going to test this is I'm going to put the positive power connection in 1 pin and move the cathode around, trying to find something that lights it up. If that doesn't work, then I move the positive pin and test if that one the positive pin was in was the cathode. If that doesn't work, we reverse it and try to see if it's anode. And if that doesn't work, to the spec sheet we go. So let's go ahead and set a current limit of 10 milliamps. I will put the anode in pin 1, and then we'll start moving around. Pin 2, 3, 4, 5, 6, nothing there. So now we'll go to pin 7, 8, 9, 10, 11, 12. No dice. So let's flip it and see. Pin 2 is positive. Now we'll put negative in pin 1. And there you go. So pin 1 is a cathode. So pin 2 controls that segment of that one. So let's start moving it around. So that's pin 2, pin 3, 4. Oh, 4 doesn't light anything up. So let's remember pin 4 for a minute, because it's not another cathode. We already tried that. So pin 4 is something else. 5. Pin 5 is also something else. 6, 7, 8, 9, 10, 11, and pin 12 is something else. So what did I say? 4 and 5? 2, 3, 4, and 5. 1, 2, 3, 4, 5. 4, 5, 12, and 1. Let's write this down. Pins 1, 4, 5, 12. 1 is cathode for digit 1, because as we went through, we found 8 segments, all right? Pins 2, 3, 6, it's 3 so far, 7, 8, 9, 10, 11. That's 5 more, is 8. So there's our 8 segments, but they were all in digit 1. That's conspicuous. So we have all 8 segments lit up with 8 pins. We have 4 pins left over. Only one of them acts as a cathode for this digit. 4 pins, 4 digits. So what if we put the cathode in pin 4? 1, 2, 3, 4. So we try the anode, the positive in pin 1. Nothing, of course. Pin 2, we're getting a light up on the second digit. So 2, 3, skip 5, go to 6. So 2, 3, 4, 5, 6. So now I've got 3, 7, 8, 9, 10, 11. And 12 is nothing. See, no wastage. It's just not conducting. It's the same pins. Is it the same segments? So let's try cathode in 1, anode in 3. Top left segment of the first digit. So let's move the cathode to pin 4. Top left segment of the second digit. How about pin 5? Top left of the third, and the last mystery pin was 12. 1, 2, 3, 4, 5, 6. Top left of the fourth digit. So now we figured it out. There are 4 pins that are cathodes. This is not common cathode for the entire thing. It's common cathode for each digit. Imagine that we have 4 separate digits. They're not connected, they're just 4, and we've plugged them in together. So each one is its own LED array. So 1 cathode for each of these segments. But those 8 pins left over, 12 pins, 4 are cathodes, 1 for each digit, and then the other 8 select which segment of the current digit. So how would you do this with a microcontroller? First of all, you'd need one with 12 pins, which the Arduino Uno that I have does have. You can use 13, and if you don't want to turn on the LED that's built into the PCB, you have exactly 12. But if you want to control it while connected to USB, you lose 2 pins for the USB, for the serial in general rather, so now you're down to 10. And in a real situation, you're not going to be using 12 data pins on a microcontroller. That's just insane. So you would have to implement your own shift register to do this, unless, like, if you're just breadboarding it and doing it for yourself and you have, some huge microcontroller with 20 pins, then you can feel free, but not in a normal situation. So this is a situation where you would actually cycle through rapidly. You know how you can dim an LED with PWM? Well, let's say we're not trying to dim them, we're just trying to light them. You can switch between segments. There are 32 segments. So let's say at one moment, you turn on, using your microcontroller, however you've got it set up, you turn whichever cathode to select the digit to 0, to low, and then you turn on the segment selector, so the cathode is the digit selector. So one of 4 pins you set to low, and then you pick a segment in that digit you want to turn on, and you set that pin to high. So you're turning on one segment, and then you turn it on for a certain amount of time. You go through all the other ones that are on, and then you do it again. And you just have to do it fast enough that the human eye doesn't notice. Common frame rates for video games that people consider adequate, 24, 30, 60, 144 is quite common now. You can definitely do it fast enough that the human eye will not notice. The faster you do it, the fewer people will notice, until it gets fast enough, nobody physically can notice that's ever been born. So that's how you would do something like this, and you would use a shift register, which we'll obviously get into later. But it's just a bit of trickery that allows you to use a few pins in sequence to control something round robin. So you go through all 32, then all 32 again, then all 32 again. So now we figured this one out, and we're not going to be able to run it directly, but with future additional tools, we don't need a spec sheet. So once again, we've reinforced the techniques to figure out how something works without a spec sheet. And now we turn our amps down for safety, so that we don't accidentally plug it in before turning it on next time and put some current to something else without a resistor that we didn't mean to. Using spec sheets is obviously the best way to do things. As one of my college professors liked to say, RTFM, read that fine manual. The purpose of doing this is not to show you that you don't need spec sheets. A lot of the time you definitely do. and the rest of the time it's still easier. This is just a way to learn how to analyze circuits. It's not so much figuring out how this works. If you just want to figure out how something works, look at a spec sheet. But you learn how to figure things out, especially if you're working with old electronics that maybe don't have easy to get spec sheets anymore. Maybe the spec sheets were only in print. Or even better, if you're working on disassembling some proprietary device, and the closest thing to spec sheets you're going to get is trying to sort through the patent office, which, let me tell you, is going to take up many of your days if you try. Reverse engineering is a valuable skill, no matter how much our government is trying to legislate against the practice. It is an excellent skill to have in your toolset. So that'll do it. Now we have our 4-digit display to go with our 1-digit display. What's left of it? What are we going to do with it? You'll have to wait to find out. Until then, be seeing you.